I'm going to start the recording, and it's 6:30, so I'll go ahead and kick things off. So welcome. This is the Triad Microsoft Data Platform User Group. We're out of the Triad of North Carolina, so right in the middle of the state, for those of you out of town. So welcome. We normally meet in person, but of course, for last year, everything's been torn upside down, but I'm glad that Ed's able to join us today from New York and learn some new stuff. So we are part of the Azure data community. So they pay for the meetup. There's some additional benefits, but if you go out to this website, there's a ton of other user groups, as well as I think Denny Cherry has a platform as well that some user groups are using. So a lot of good content out there. If you didn't know, Redgate purchased all of past assets, and all their recorded videos are underneath SQL Pass TV. And so I just went out there and looked, and they have from 2020 all the way back to 2013. So there's a ton of material out there. So be sure to go out if you are looking for some past materials. Even if you didn't purchase the recordings, they're all made available for free. This is our YouTube channel. So you'll find us out here. We just started recording these at the beginning of the year. So think like the SQL engine, we had a Synapse session, and then Brandon Leach did a session on corruption. So, we're just getting started. Redgate also released underneath their educational series, all of the Pay for Pass Pro content is underneath the educational series, besides other things they have available on their quote university site. So be sure to check that out. There's some good content out there as well. And then Tech Systems, I don't know, did anyone from Tech join the call? So usually we meet at their offices in Greensboro, and they're a staffing firm for IT and other industries, but we've had some good luck getting jobs from them. And I know others have had good luck getting, or we got candidates from them, and then others have got good luck getting jobs from them. So if you're in the market, give them a ring. And then O'Reilly, Apress, and Pluralsight. For those of you who may not know, it's almost over, but Pluralsight has been free all month of April. There's a few days left. So if you're interested, you can sign up there. Apress has some really good books out. It seems like a lot of the SQL Server community folks are using Apress. So a lot of good stuff out there on Azure and that kind of stuff. And then O'Reilly has their Safari books online that you can get a trial as well. So if you're interested in that, head out over there for a trial. And then now I'm going to pass it over to Ed. So he's going to talk to us today about improving analytics performance with Columnstore indexes. So I am going to stop sharing and let you get started.
Thank you very much. Can everyone see a PowerPoint thingy?
Yes.
Great. Awesome. So thank you very much for having me today. I really love speaking to new groups I haven't spoken to before and meeting new people. And then, as I kind of talked about earlier, eventually, hopefully getting to meet you in person at some point in the future. Either maybe you'll come up here, or I'll go down there, or we'll meet somewhere else, elsewhere. You never know. I've met very interesting people at faraway places, like, in Montreal or in Toronto or in California. So you never know where you meet people. Anyway, this presentation is all about Columnstore indexes. It's a topic that I love. I love using them. I have made great use of them in production environments. I play with them on my own to store my own data. Things I used to store in regular old tables that stunk, I put them in Columnstore indexes and structured them nicely, and now they're very, very fast. This is a wonderful feature of SQL Server, originally released in 2012, but not great. It was read-only. They were made writable in 2014, but they still had a lot of limitations. And then from 2016 on, they've been making them a little better in every version and adding more and more features to make them just more usable and more powerful. So this is all about those. Who here has worked, by the way, with Columnstore indexes before, or has an interest in them, or has played with them? Just kind of curious. Some hands? Cool. Whether you've used them or not, they're wonderful tools. This is me. All of my info at the end in case you want to contact me. I live in Albany, New York. It's actually beautiful here finally after like 27 months of winter. I have my family here who right now is pretty quiet. I'm actually concerned if they're alive, but hopefully they're alive. And I've published several books, as well as some chapters in books. I've written a lot of articles. A-Press actually published my books, so I have a lot of stuff out there. I'm not going to go into a lot of detail now. You're more than welcome to look me up. I organized SQL Saturday Albany. We're taking a year off this year, but we did 7 years straight before then. And I've attended a lot of events and seen some of you over the years and other people. Hopefully I'll see you soon at future events. While I'm going at this, feel free to stop me if you have any burning questions. Otherwise, at the end, we can take them then, whatever's easiest for you. If you want to stop me along the way, it's like a freight train. Just jump out in front and wave your arms, and I'm sure it'll be fine. All right, so what are we going to do? What I want to do is do a quick review of just Olap data. What is it and where can we store it? Do the brief intro to Columnstore indexes, and then kind of dig into some more details about their architecture and best practices and what are the maintenance options for them and other ideas. And so I can't cover everything, but I try very hard to at least briefly hit the important topics. And then if you want more detail, feel free to contact me later or hit up the web. There are other good resources in the web for Columnstore indexes, in addition to me. I do have articles out there on it. Feel free to read up on them if you want. So the first real question we ask is, and this session is exclusively really about Olap data, analytic data, the kind of big stuff you aggregate and store for reporting purposes and analytics purposes. We're looking for insights and the data might get big. And we have a lot of options of where we can put it. A common choice people take today is unstructured. I don't want to take my data and throw it into a place. I don't want to structure it. I don't want tables. I don't want primary keys. I want to chuck the data somewhere as it is and then dunk into it when I want it. And for things like that, Hadoop or data lakes or Hive or whatever, those are great options. There's many, many more out there too. And those are great if you don't really know what you want, if you don't have common questions you ask regularly, if you don't have frequent reports or analytics that you run often. Unstructured data is really good if you just don't really know what you're looking for and you want to begin just playing. If that's not the case, though, it may not be the best option, depending on what you're looking for. There's many data warehouse products out there. Microsoft provides analysis services. Amazon has Redshift. There's many, many more products out there that will take your data and turn it into a warehouse, and you can then access it and use it and do things. The plus side is they've built your whole warehouse system that will handle your data. The downside is you got to learn their system, and it may or may not be easy. Like, for example, analysis services is a powerful tool, but it requires learning MDX or DAX and learning all the intricacies of how to get data in and out of there. And it's not simple. So you may or may not want to do that, but you may support it as well. If you want, you can go outside and open your door right now and step outside and yell really loud, "Hey, I have some big data to store, but I don't know where to store it. Help." And salespeople will descend upon your house like flies and try to sell you things, I promise. There's lots of third-party analytics software out there, and some is very powerful, some is very good, but not all of them have very direct purposes, and not all of them may fulfill your purposes. And so if you are looking at any point to find a third-party software, cloud-based software, whatever, to handle your analytic data, just know exactly what you want before you dive in and begin talking to salespeople, because I've seen a lot of people just get taken through the ringer because their data was slow. They didn't know why. They talked to some salespeople and suddenly they're, in $1 million contract and that's what the heck they're doing. So third-party software is cool, but again, there's vendor lock-in, there's learning their software, and there's the question of, will it do what I want to do it? So may or may not be good. If your data is small, if you're not really sure what you're doing with it yet, but it's small and manageable, you can put it into OLTP tables. You can simply take your data, put it into a classic transactional table with a clustered index, whether it's in SQL Server or in some other relational database, and just use it. For small tables, for lookup tables, maybe slowly changing dimensions that don't get very big, that's fine. Like if you have some metadata table that has 100 rows in it that you update daily, you don't need anything special for it. Just throw it in a table, give it like an index, call it a day. But once your data gets big, this becomes problematic. When your data hits millions or maybe tens or hundreds of millions of rows, just throwing it into a table with some indexes on it may not be good enough, especially if you're trying to aggregate lots of it. If you take a classic table and throw 10 million rows in it and then you say, oh, I need a sum of this column over 1 million of those rows, you're probably going to wait for it. Heck, even a select count star from a classic cluster index can take a while. So OLTP tables are great for small. They're great for very organized and not too big. But once you get too big, they begin to get slow. And that's what we've been asking, what should I do with my data? It's gotten too big for this old, what I was doing before. And the reason is because your transactional tables are built for row stores. You insert rows and they get stored row by row by row on pages. Column 1's next to column 2, next to column 3, all in a chunk, followed by the next row. And so when you read data, you're reading rows and you're reading pages that contain rows. And because of that, if you need to get, let's say, the sum of a million values, you've got to grab a million rows of data first, or a million rows from an index first before you get what you want. So that leads us to what this presentation is about, and that's Olap tables in a relational database, specifically Columnstore indexes in SQL Server. Other products out there like MySQL and Oracle do have their own Columnstore technologies. We're going to talk about SQL Server. If you're using other technologies, though, out there besides SQL Server, there are options. You can look them up. They're available. And as the rest of this presentation is about, is Columnstore indexes and storing your data into analytic tables inside of a relational database. All right. So what is a Columnstore index? This is a good question to ask because it's not just an index. A Columnstore index is a specialized Olap data structure, and it's meant for big data. When I say big data means different things to everybody, but when I say large data sets, I mean you're talking about row counts into the millions, tens of millions, billions. If you have less than a million rows, you're probably not going to gain much by a Columnstore index unless you're simply scanning the whole thing all the time. If you have a million rows, you scan it all the time, maybe it's fine. But in general, you want many millions of rows before you consider using this probably, and ideally ordered by time. But what this can do for you is make your data much, much faster. And when I say 10 to 100 times faster, it's not a joke. Microsoft is not being sarcastic. They really meant that. You really can make your queries that much faster. And the technology behind it isn't just an index. The technology that powers a Columnstore index is the exact same stuff used by all the rest of the analytics software in Microsoft stack. So if you use Power Pivot or Power BI, or you're doing stuff inside of Excel or whatever, that data is stored using very similar technology. And essentially what it's doing is taking the data, breaking it up by columns, and crunching the columns individually, which can do very efficiently. And because it's natively supported in SQL Server, you get it automatically. So when you buy SQL Server and you pay for a license, it's there for you. You have Developer Edition, Express Edition, whatever, the Columnstore indexes are there for you, and they work. So because they're already included, you don't have to pay for more software. It just works, and you can natively support it within all the rest of your data. You can have it in a server, there's stuff on it, and it'll work fine. But the key takeaway really is that it's not just an index. Like when we think of indexes, we think of non-clustered, clustered, filtered, XML indexes, but that's not what this is. It's a totally unique structure, and I'm going to describe it in detail. And then we'll have lots and lots of demos because live demos are fun. They can break. Anything that can break is exciting. So we'll have lots of that along the way. Cool. And before I dive in, does anybody have any questions at all? Or are we good to just charge forward? I see nobody coming off mute, so I'll assume that charging forward is the right choice. So number one, why are Columnstore indexes fast? I'm going to try to answer that over the next handful of slides. But number one is compression. Because they take the data and group them by columns, you can compress it very heavily. Classic compression is effective, but row compression and page compression is forced to take all of your columns of data and mush it together. And it can do a good job of compressing, but at the end of the day, if you take a single column of data and take a million rows of it and say, hey, here's a column, it's going to probably have a lot of similar values, and they'll compress amazingly well. For example, so you have a column that has a lookup value in it, and there's 20 possible values. You have a million rows of it. Well, 20 possible values, a million rows, that's, 50,000 rows a piece? That will compress into nothing. Even if it's a giant varchar or something, it'll compress beautifully because you're just repeating the same things over and over and over. The more repetitive your data, the better it compresses. And that data will remain compressed, just like page and row compression. It'll remain compressed until needed. So it'll be compressed on disk in your storage system, wherever it is, and it'll stay compressed in memory, wherever your memory is, in a VM, in the cloud, wherever the heck your memory is, it'll stay compressed. So until you need it, it's nice and tidy, and that's wonderful. So once your data is in memory, getting it is very, very fast. So really quick, I have lots of demos today. I'm in wide world importers, but I pretty much built all my own stuff. I've already built all the tables, and I've already populated them and built the indexes because I made them a little big, and you don't want to sit here and wait for me to build an index for 20 minutes and then do it again and again and again. So I'm going to build a lot of tables here, but they're already built. So I'll describe what I've done already, and then we'll demo against it and show how it works. So my initial demo here was a classic PK clustered table. So you have some big int key, you got a bunch of columns, and I insert a mountain of data into it. I put a non-clustered on it to kind of simulate the whole ordering by date thing. And then we can look at our data. So if I look at it, even just a simple query here takes a moment to execute, 2 seconds, and it took like, 49,000 reads. You can see that I have here a range of data going over 20, 30, 4 years, and there's about 23 million rows. So not giant, but not tiny. Big enough for some fun demos. Cool. That's our first demo table here. It's the PK cluster index, classic table, nothing special. All right, next table. This is going to be a page compressed table. So same exact table, but I added page compression to it. Really just to demo how big will it be. Everything else is exactly the same data, same additional index. We'll come back to that in a sec. Next, here is a Columnstore index table. So this is where it begins to get interesting. Same table, same columns, no differences. I didn't change any data types on you here, nullability or anything, just exact same table. The only difference is I build a table, I insert a mountain of data into it, and then I plop on a clustered column store index. Now a clustered column store index, you don't specify a column list. So when you put a clustered column store, this is truly indeed like its own data structure. You don't specify columns, it will automatically build the whole table column by column and compress each column separately into your index. So the whole index, the whole table is one index now. And that's it. This is how it works. And that's nice. So the whole thing's compressed beautifully now into a column store index. So now I can ask again, how much data do I have? Notice this came back a lot faster. And I got my same data back. Same start date, end date, same row counts, done. So the question now, of course, is how big is this? How big does this data get? So this query I'm going to run here, feel free to steal it and use it in your own time if you want. I'll share all the, I'll email you back afterwards with the slides and the demos so you can steal them and use them. Feel free to steal them and use them. Have fun. So this query here, all it's going to basically do is just go through each table that I specified here. Let me get the page compressed one too, actually. I didn't include that, and that was negligent of me. So we'll just scroll down and type a few things while I'm going because, what can possibly go wrong there? Okay. So we'll run this, and this will go through and tell me our table sizes. So we can see here that the original table with no column store, no compression is about 5 gigs. About 4.6 of that is data, about 500 megs is index, and it's about 0.2 KB per row. If I page compress it, it actually compresses pretty well. It goes down to about 2 gigs. That's pretty cool. But then if I column store it, I just slap the column store index on, no optimizations, no best practices, no thinking, just slap it on. It goes down to 340 megs. So that's a pretty big difference. Now you notice the data space is the same about. There's a round off error here because I did some rounding up there. And then index size is 0 because I have no additional indexes in the table. The column store index is the actual stored data, and that's it. So you can see that the factor of improvement here is like, about a little over 2x for the page compression, but like 15x for the column store index. And you're probably thinking, wow, 15x improvement is pretty good. And we're going to do a lot better later. So I just wanted to kind of illustrate up front, like, here's how you create a column store index. The creation is very simple, not complicated. You don't have to know really exotic SQL or anything. And the immediate benefit is apparent. You get amazing compression. I squeezed 23 million rows into like 300 megs. So immediately out of the gate, really good compression, but we're going to do better in a little bit. So that's just the overview of what does it look like. What are some of our demo tables going to look like? Cool. So what else makes column store indexes fast? They compress by column, and I'll go through the architecture of that in a little bit, but there's more that makes it fast. The next big thing that makes column store indexes fast is that when columns are compressed, SQL Server stores metadata in line with it. And it's not like the metadata in statistics or in indexes or in other structures where it may fall out of date or may not be used for optimization. The metadata stored with the column store indexes is kept up to date, and it's used by the optimizer to get good plans. And so it automatically knows for each chunk of data that it compresses, mins and maxes and counts and things like that. It knows basics of what values are in there. And it can use that for filtering. So if SQL Server knows that a chunk of data in a column store index, and I'll describe what a chunk is soon, so I'm not using the word chunk because chunk is kind of a silly word, but it ultimately allows you to filter very quickly and do math on your underlying data because you already have common analytic metrics like mins and maxes and counts already calculated for you. And so when you ask SQL Server to do it, it doesn't say, let me scan 10 million rows. It can say, hey, that data is already in memory and I have the metadata. I'll just use the metadata and be done. And so it can be very, very fast because of that. In addition, somebody mentioned earlier before we started about batch execution, how cool batch execution is. And it is very cool. Under the covers, classic SQL Server queries process rows row by row. You may update 100 rows or select 1,000,000 rows or do things in a set-based fashion, but classic SQL Server before batch execution, under the covers, when rows are passed from operator to operator in the execution plan, did it row by row. And that's just how the engine worked. And then they began introducing about 5 years ago the idea of batch execution, and that behind the scenes, SQL Server can take and pass groups of rows from operator to operator. And this is not parallelism. This is simply batch execution. You don't need parallelism for this to work. And so what SQL Server will do, will say, oh, you're reading 10 million rows. Well, instead of reading 10 million rows one at a time behind the scenes, we'll batch them into kind of groups of maybe 100 or 500 or 1,000 and pass them from operator to operator. So under the covers, it's passing more data through your execution plans faster, and therefore your queries execute faster. So typically this is great against large data sets. When you have more data executing large queries, this makes great sense. And it's easy to check in the execution plan to make sure it's happening. And you don't have to do a whole lot to make it happen. It's automatic. That's the beauty of it. So as long as SQL Server believes it's the right thing to do, it'll do it. And you can check it pretty easily. You can turn on our actual execution plan, and I can simply run a query, like just some analytic query. You know, give me some basic metrics for all the rows greater than 1/1/2016, and I'll get it back. And this is against my Columnstore index table. Came back in a second or so. You know, I can see my reads and writes in the table, and there's my execution plan. Did a Columnstore index scan, which, by the way, you're looking at execution plans for a Columnstore index, you will always see Columnstore index scan. You'll never see seek or lookup. It'll always be a scan. That's just the name of the operator. There's actually an open connect request to Microsoft for please make it more specific, because scans scare people and everyone thinks scans are bad. But for Columnstore, scans are not bad. So when you see this, do not fear. That's simply the operator used because under the covers, in the engine, it's just scanning segments of data inside of a Columnstore index. It's just how it works. But you can see if you hover over the operators, you'll see batch. So actual execution mode batch, estimated mode batch. You know right off the bat that when this was processing this query, it sent through the rows and groups, and it was faster because of that. It's always faster when you use batch mode against a large data set. And typically, SQL Server will choose batch or row, and it'll choose it effectively. If you have a scenario where it's choosing the wrong one, maybe you have a stats issue or some other settings issue possibly out there, or you have a very poorly indexed table. There's reasons for that happening, but it's rare. And against Columnstore indexes, it's very, very rare, because against Columnstore, SQL Server knows batch is usually the right thing to do. So I won't go into it any more than that, than just say you can check all the operators and you'll see for each one whether batch or row is used. Cool. Until somebody stops me, I will keep charging forward, just head first, until I crash. There'll be no crashing, I don't think. Next key. So I've talked a little bit about reads and how fast you can compress the data and read the data. But one cool key to speed with Columnstore indexes is that they can bulk load data. So traditionally, you could like BCP data into a table from a file, and you can make it really, really fast via a minimally logged process. And for a large data load, minimally logged made a lot of sense, because you're just bulk loading a pile of reporting data, and you know as an operator or an architect that if the thing failed for some reason, you would simply say, run it again. You wouldn't think about it, you wouldn't fret, you would just say, do the thing again. And so bulk loading means that if you insert a large number of rows into a Columnstore index, it won't insert them one at a time. It won't have a giant pile of transaction log bloat. It'll simply say, oh, you're inserting a lot of rows, and I will specify what a lot means shortly. Okay, we'll do it for a minimally logged process. And because of that, it'll happen faster, because you don't have to log the whole thing. You know, classic tables, classic scenarios, when you insert a lot of data into a table, you've got to log it. And that can cause transaction log bloat. It can cause contention while you write data to a table. Anybody here ever like build a process to write data to a table or update it and did it in batches because we were afraid of causing contention and locking and deadlocking? Yeah, there's always a hand there, because you don't want, if you're a busy transactional system, you may say, you know, I'll do 1,000 rows at a time and wait, because it's better to wait and have little transactions than, you know, cause a huge mess in the table where everyone's waiting for me. Column store indexes are the opposite. For a column store index, you want to insert a lot of data at once. Inserting 1 million rows at one time or 10 million rows in one operation will probably be faster, significantly faster than inserting 1,000 at a time or a small batch. So you have an incentive for a large Olap data load to just do it. You know, insert 1 million rows at a time, go, no problem. That will be faster. So I've kind of given the overall, like, here's why they're faster. And there's other reasons, but those are the main reasons why column store indexes are faster for large analytic data sets. So how do they look under the covers? By describing the data sets and how you best use them, we can really arrive at what is the ideal target data for a column store index. When should you use them? And when should you not use them? And it's a good question to ask, because you should not use them for everything. There are many scenarios where you don't want to use a column store index. They will not be optimal. And there are many cases where they are great. So under the covers, the way a column store index works is that it takes your data and breaks it into what's called segments. A segment is just a column, and then it breaks it into row groups. A row group is just a collection of rows. You have to basically break down your column store index into groups of rows, and a row group in SQL Server is up to 2 to the 20th rows, or about 1 million rows per row group. You can do 2 to the 20th out in a calculator. I'll just call it 1 million for simplicity's sake. And so each row group has about 1 million rows, and each of those groups of 1 million rows will have each column separately stored in what's called a segment and highly compressed. And each segment will include within it some metadata. And then you can query that row group and learn about that metadata and what it is, or query the segment and get metadata about that segment. And so when we talk about column store indexes, we're going to talk about row groups and segments. And this is kind of what it looks like. And so each segment is separate. When you read data into memory, you're not reading indexes, you're not reading row groups, you're reading segments. It's all you're doing. So how does this work? How do we use this structure? What does it even mean? And the answer is that because each of these little blocks you see here on the screen is an individual unit, you can read them from storage and from memory as individual units. I don't have to read an entire column or an entire row group to get what I need. And that's huge. So another huge thing about this is that all the metadata surrounding this is available in SQL Server. You can simply look at it, read it, examine it, and learn about it. You can report on it. So I've already built one column store index, and we can look at the row groups for that column store index. So you can steal my query later. Ultimately, there's only really one new special view here, and that's sys.columnstore row groups. It has one row per row group. It tells you about how your rows are stored within the column store index. And I just joined a bunch of other views here to get other metadata from SQL Server. Again, feel free to steal my queries. I don't mind. And so I'm getting it from my one column store index. I do that and I get back 23 rows. Remember earlier, it was about 23 million rows in the table, 23.14 million rows. And I see here I have 23 row groups of about 1 million-ish rows apiece. So the numbers kind of make sense. You can see that each one has about 2 to the 20th rows in it, has exactly 2 to the 20th rows, until we hit the last one that has the remainder. But you can see here, each row group has an ID. You can see the size in bytes. You can see how many rows are in it. And that's cool. Those are the row groups. Next are the segments. And so within each row group, it's a segment per column. If you have 10 columns in a table, then you'll have 10 segments per row group. So again, there's one new view here called sys.columnstore segments. And these views are very well documented. If you don't like what I've provided here, feel free to go to Microsoft. They'll give you their own garbage documentation you can use too, I promise. But these queries are pretty useful. And so here's every segment within, did I delete it all? I did. Every segment within the table. And you can see here, if you start scrolling through, there'll be 23 rows per column. In other words, each segment for each column has one of them in every row group. So if you have city key as a column, you'll see 23 segments, one per row group. And if I scroll down, I'll see that's the way it is throughout this thing. 23 segments, one per row group all the way through, for a total of 437 segments. And each one of these is individually compressed, and more importantly, the metadata is here. So you can see for any given row, you can see there is a has nulls. You can see some basic IDs to identify it, the partition it's on, if you want to check storage, and then mins and maxes. These mins and maxes are huge. This tells you the minimum data ID and maximum data ID. If it's numeric, you'll just see a number here. If it is a decimal or a string or some complicated data type, there'll be a lookup that goes to a dictionary. But you can see mins and maxes. And then, like, for the sake of its own calculations, the null. And then what's the size of each segment? You can see some are kind of big and some are kind of tiny, depending on the data type. If it's a decimal or an integer or a bit, it'll be pretty tiny. If it's not, it can be kind of big. But again, big is in quotes. It's way smaller than what you would store in a standard index. Cool. So we have lots of metadata stored with each segment on our data. And that metadata can be used to solve queries, to actually create execution plans and simplify queries. So when you say, give me, you have a 100 million row table and you want 20 rows for a given date, SQL Server can look at the metadata and immediately say, oh, I know that only exists in these 2 row groups. I'll just grab that data and ignore the rest. Poof, done. And you can't do that with standard tables in SQL Server. So that's pretty cool. But now here's the power of it. So you've seen the structure here that I built. This is kind of my demo table here for the sake of pictures of 6 columns and 4 row groups. But let's say that I only query my Columnstore index for columns A and B, and that's it. I don't have to grab C through F like a traditional index. If I go to a traditional clustered index, everything comes along for the ride. If I have 10 columns, I've got to grab 10 columns of data to get my 2 columns. That's just how it works. Here, what will happen is SQL Server will say, oh, you said select column A and column B only. I will just grab column A and column B, and C through F will be ignored. I won't read it into memory. I won't read it out of memory. I will ignore it. And so right off the bat, by querying less columns, you will read less data without the need for any additional indexes or tricks or tips or optimizations or stuff. Just automatically, this always works in a Columnstore index no matter what. If you query for certain columns, you get those certain columns and nothing else. Automatic. No tricks needed. That's one form of elimination. The next form of elimination is row group elimination. So because you have metadata stored in every row group, you know for each of those row groups, 1, 2, 3, and 4, the min and max values for each column, A, B, C, D, E, and F. And if you know that information, you can eliminate row groups that don't have data that fit your query. Now, in an optimal scenario that I'll talk about soon, ordered data will perform better. If your data is totally random, it'll be very hard to make that work. But if your data has some kind of order, usually by time, and I'll describe that soon, then it'll do better. Let's say that I were to query for data that was only in row group 1. Let's say I queried for a very narrow value of column A that only existed in row group 1 because the metadata said so. Like I know the column A just happens to have values 0 through 10, and the rest of the row groups have higher values. SQL Server will automatically consult the metadata and say, I know that only row group 1 has this. I will skip 2 to 4. And so because it knows that, I will only return 1 row group. And this is very powerful because as your Columnstore index gets bigger and bigger and bigger, tens of million, hundreds of million, billions, tens of billions of rows or more, those row groups become more important, and that elimination becomes more important. Because traditionally, when you query your big mountainous Olap data, you're usually not going to say, give me all the data. You're going to say, give me the last year, the last month, the last quarter. And when you do that, SQL Server knows automatically, well, hey, if you only want the last quarter and I have 10 years of data and it's ordered by date, which typically your data will be, right? You throw data into your table in order by date. It'll know to ignore all the rest of the data. And if you have 10 billion rows, it can pull just the 100 million rows you need and ignore the rest. Of course, the real power is when you combine them. If you say, hey, I only am going to query for this small date range, small in quotes, it could be big, it could be millions of rows, whatever, but I'm going to query for a smaller date range, and I'm only going to query for columns A and B. Well, suddenly, my 24 segments of data becomes 2. And querying for 2 segments in a Columnstore index is like lightning. And this is how most common Olap queries work. And these are the queries that will get given the most benefit from a Columnstore index, where you say, hey, give me a count or a sum or a min or a max over a time frame for some columns. Those are common analytics, and they'll be very, very fast in a Columnstore index, lightning fast. You will be shocked at how fast they are and be amazed. Those are the optimal use cases. You don't have to query through the optimal use case. Select star from a column store index will be slower, but if it's only over a small date range, it'll still be very fast due to compression. There's one more structure in the architecture of a column store index worth talking about, and that is the delta store. So because the column store index is highly compressed, the process of writing data to it is expensive, and you simply can't write data to it all the time. That was why the original column store indexes back in 2012 were read-only. And it was why when they made writable in 2014, they had tons of restrictions because writing data was expensive. And if you said, write one row, you got to decompress the column store index, put a row in there, recompress it. That is really expensive, and that takes a lot of time. You're taking 1 million rows and doing a ton of stuff to it. So what was added to SQL Server to make it faster and to make it writable was something called the delta store. The delta store is basically a heap. It is a B-tree heap. And don't be afraid of it. It's a good thing. And so what happens is if you insert tons of data, like millions of rows, hundreds of thousands of rows, you'll get a nice bulk insert into your column store index. It's beautiful, it's fast, it's minimally logged, it's awesome. But you can't always do that. Sometimes you will insert 100 rows or the remainder of a data load, and you'll insert less rows. And if you do that, it'll still be fast. What will happen is SQL Server will take those 100 rows and throw them into the delta store first. Toss them in a heap. That's it. When you read data out of your column store index, it'll take what's in the compressed segments in your delta store and combine them to get your final view of it. And it may sound slow, but it's not really that slow because typically the delta store won't have a lot of rows in it, and scanning 1,000 rows in a heap isn't that bad, really. And then what will happen is as data accumulates in the delta store, automatic processes in the background will take that data and push it to the column store index when convenient. You may ask how many rows, what are the details, and there are some metrics in that, but much of how it operates is kind of internal to SQL Server. You don't have to worry about it, and that's a good thing. You can force the contents out of the delta store using index operations like a reorg if you really want to, but it's optional. You don't have to. It'll speed up your queries by like 0.05% or something, so it'll matter, but it won't make a huge difference. But the real key of the delta store is that this is really important towards making writes work fast because you don't want to write data to a column store index row by row by row. You want to do it in batches if possible. And if you're not doing it, SQL Server is doing it for you. Cool. So I'm going to move into kind of the operations and how each operation, each write operation in SQL Server works because it's important to understand how it works. Like when you're taking large data and writing to a table, doing it in an optimal fashion is really important. So I start getting to best practices and optimization and making these as efficient as possible. So insert operations that are small, typically under the 100,000-ish row mark, will just be inserted into the delta store. And they'll sit there, and then SQL Server will either asynchronously push the data to the column store index when convenient, or you'll keep inserting more data, and eventually SQL Server will say, oh, we've got a mountain of data there now. Let's bulk insert that into the column store index. So it'll try to bulk insert if it can. If it can't, it'll eventually put it over there. And so in general, the big takeaway from insert operations is there's a benefit to inserting large data in big batches. Don't be afraid to insert 1 million rows at once. 1 million's kind of like a nice number. You can optimize it perfectly if you're a nerd and you can say, I'll do 2 to the 20th rows at a time, but you don't really have to. There's no huge difference in the long run. But writing rows in the millions should not be feared. It'll be minimally logged, it'll be very, very fast, and it'll make your data loads go much faster. So whatever traditional data load process you have right now that loads 10 million rows into a column, a clustered index, classic index, this will be 10 times faster. It'll be amazing. You'll love it. Delete operations and update operations are different though. So inserts are awesome. Inserting data into a column store index is super fast, super easy, and it embodies the word awesome. Write operations otherwise though are less awesome. So delete operations are fast, but they're only fast because you don't actually delete the data. Again, decompressing and recompressing the cluster, the segments is expensive. So we don't want to do it very often. So instead of doing it very often, what we'll instead do is soft delete them. And I'll show that to you in the metadata shortly. So what basically happens is the first time you delete data from a column store index, it'll build what's called a delete bitmap. This is another heap, just a B-tree structure, a giant heap that sits on top of the column store index. And all it is a bunch of bits that say which rows are deleted, and that's it. And when you read from your column store index, It'll merge it with the bitmap really fast, and anything that's flagged as deleted will be ignored. So it's basically a filter. So all deletes in a Columnstore index are soft deletes until you run index maintenance. This is not necessarily bad, but frequent delete operations will cause fragmentation over time that a reorg or maybe even a rebuild, if it's really serious, can fix. If your delete operations are ordered, like I keep a year of data and then I slowly remove the last data that falls off the year, you won't see that much fragmentation, kind of like in a classic a transactional table. But if you're deleting data from all over the place, you may see fragmentation over time as you begin soft deleting data everywhere. And if you want to read 1 million rows and you just have 1 million rows of data, you read one segment and you're done. If you want to read 1 million rows and you've deleted half your data, well, now you're going to say, I want 500,000 rows from here, 500,000 rows have been deleted. Now I get 500,000 from here, and the rest have been deleted. Now you're reading more segments, and you're reading more data. And so you're reading all that deleted data into memory, including delete bitmap, and analyzing it. So as time goes on, you'll see fragmentation potentially, but in general, deletes are fast though, and that is important. Anybody have any questions here? I see some chat. What happens if you truncate a table? Good question. A truncate in the Columnstore world is just like a truncate in the regular old world. You truncate it, it's gone. It empties out, poof. It all vanishes. So truncates are very, very fast. And I'll talk about some truncation tricks later for larger tables if you're interested, like in partition truncation and such. But a truncate is the way it's always worked. You do it and you pray you didn't misuse it, because when it's gone, it's gone. It's minimally logged, it's poofed. But it is very fast. So as are deletes. Deletes are fast, but they can cause fragmentation if you're doing unordered deletes from all over the place, kind of like a regular old index. So how do deletes work? Let's take a look at a table here. So I'm going to take a peek here at my table from earlier. This is fact order big CCI, and I can see here all 23 of my row groups. And you'll see right in there in the metadata, I have my row count, my size, and deleted rows. There they are, right there. In this metadata, SQL Server hands you in a silver platter. It tells you right here how many rows are deleted. So you know right now how many are deleted and their approximate fragmentation right off the bat. Let's say I go and I delete some rows. It's pretty fast because it's not really deleting them. It's just soft deleting them. It just took 100 rows and it flagged them as deleted. Poof, just bitmap, flagged one, done. As a side note, it was a little slow. It's like 1 second because it had to build the delete bitmap first. For future deletes in these segment and the row groups will be faster. Now, if I go back and run the same query as before against my metadata, I can see now that I have some deleted rows here. I have 23 row groups, but I can see that I have associated with this partition 100 deleted rows, and it tells me the partition ID of where that delete bitmap is located. And so as I delete data, I can see how many rows are deleted. And so I can see I have 104 million rows, of which 100 are deleted. And that's not bad. That's a tiny fraction of a percent of my data is deleted. In my mind, that isn't very fragmented. I don't really care. That's fine. But you can see very easily what data is deleted, and that's kind of cool. Now for the hairy stuff. Update operations are messy. So an update operation in a Columnstore index is kind of like it is in a standard index. It's a delete followed by an insert, but it's got to be in a transaction. A Columnstore index may be an analytic structure, but it's still transactional. A Columnstore index still obeys ACID. It still has transactions, and they're atomic, they're durable, they're consistent, they're isolated, and that's very important. And so you do want that potential. You don't want corrupted data getting into your giant analytic data. That's important to you. But it is transactional in nature. And so you do an update, it's going to delete data, therefore create a delete bitmap, flag things as deleted, and then insert data back into it all in one transaction. And that's messy. And because you got to do all that on the fly, it gets slow very, very fast. On a smaller index or with a small row count, you'll find that updates will be kind of okay. But if you have a very, very large Columnstore index, or you try to update a large volume of rows across many row groups, you will find it gets very, very slow because now you're writing to many segments and many row groups all at once. And the more segments you write to, the slower it gets. And it can get very, very slow to the point of being like buggy. Your temp DB fills up kind of slow. So in general, it's worth saying you shouldn't run update statements on Columnstore index. And I'll talk about this a little more later as a best practice, but avoid it. Don't do it. It will be slower than you want it to be, and it'll be scary. We can demo an update really fast. This index is not that big, so it won't take that long to run. We can run our query from earlier again and see, here's my table from before. There's my 100 deleted rows from before, and there's all the rest of my index, just like before. I can go in and update the quantity on 5 rows. Done. Really fast because I didn't really update a lot of data. I updated 1 column. Cool. I can go back now to my Columnstore index and see what happened. And I can see now that I have an interesting scenario here. I have in my row group 0, same row count. I have 105 deleted rows, 105 are in delete bitmap, and 5 are in the delta store now. I'm joining over to the internal partitions table to get the details of the underworkings of the Columnstore index. So you can see internally, this is getting more complicated now. My 1 row group here has 105 rows that are kind of in this strange limbo of some are soft deleted, some are in the delta store. And again, 105 rows out of 104 million is nothing. You can read this data fast, you can write this data fast, but this will accumulate over time. And if you imagine a table where I do this to millions of rows or tens of millions of rows, it will get painful. So I'm going to talk a bit more later about the best practices and why you should never update data in a Columnstore index ever. And just trust me, it's a bug, it's scary, you can break servers with it, or just have really slow processes, but you don't really want either. The takeaway is when you don't run an update, if you've got to run an update on data, do a delete followed by an insert. It sounds stupid, but it'll be a billion times faster, you'll be happier. Maybe not a billion, but a lot. Any questions so far? Are we doing good? And I will keep an eye on out of my corner of my eye for the flashing orange chat window in case you do have questions. I'll take a peek every so often. I can try to answer. Or I can keep
doing great. Nice work.
Well, thank you. That wasn't a question, but that's cool. It's the easiest question to answer. I just nod my head and smile. I love it. Cool. So this is a really, really important best practice. This is probably the most important best practice of a Columnstore index that is not well documented by Microsoft, but is pretty well documented by the community. And that is that the Columnstore index clustered is in your entire table. And the same is true for a non-clustered. You'll specify columns in a non-clustered, but the data is not intrinsically ordered unless you order it. And so because of that, if you simply take a mountain of data and shove it into a table and throw a Columnstore index on it like we did before, right here, right now, it won't be ordered. And because of that, all that metadata in your row groups can't actually help you that much. So order is not defined by default. The order is whatever you give it. And row group elimination requires on some sort of data order, whether you supply the order or it happens naturally over time because the new data gets slapped on the end. You need to have data order for row group elimination to occur. In other words, if you want your Columnstore index to be blazingly fast, you need data to be ordered. Typically, it'll be time. For most Olap data, for most analytics stuff that you do, you're going to order by dates and times. That's pretty typical. You might have some tables that order by other stuff. And if so, this counts for that, order by that. But most time it'll be time. You'll have some sample time for your data, sample date, whatever, and you'll put new data in every day, every hour, every minute, whatever, and there you go. And so every day you slap some data on the end in some brand new row groups, and you keep tacking more data on forever. Well-ordered data will make your data smaller, faster, and more efficient in many, many ways. This is really worth demoing, and it's worth remembering. This is huge. If you want to take Columnstore indexes to the next level and make your data really, 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 really fast, this is 100% key. If you take away nothing else in this presentation, and you're going to use Columnstore indexes, and you order your data, you will do yourself a huge favor, and it's awesome. So let's go back and look again at our metadata from before for 1 column, order date key. Now dates are encoded. You won't see an actual date here. It'll get encoded off to a dictionary lookup somewhere, but we can still look at it and note that I have 23 segments here, 1 per row group, and the min data ID and the max data ID is the same for every row group. This tells me that there's no data order, that every row group contains a mishmash of dates from 2013 to 2016 with no order whatsoever. Even that last row group that has only 72,000 rows in it has no order. So If I said I want all the data from 2016 January, it's going to have to read the whole Columnstore index to get my data. Now it's still compressed. It's still kind of fast. I still get segment elimination, but I still have to read every single row group to get what I want. And that's not great. That is not optimal. So for example, say I ran a simple analytic query here. This is a common analytic query. Hey, give me a sum of quantity for the past month, go. This should be lightning fast, and it is because it's a Columnstore index, but I can check, and there's my answer. It came back fast, but I can look at my statistics IO. So at the beginning of this, I'm on row 430 here. I turn on set statistics IO on, and that will give me my stats. How much IO am I doing? If I look at this, the output, I will see that it scanned my Columnstore index. It had 3 logical reads, some 17,000 off-page reads, which is what most of a Columnstore index is, which isn't bad. But the reason it was so high, the reason why this number was so big, 17,000 reads, is because of this. It tells me right here, every time I do stats.io for a Columnstore index, how many segments I read and skipped. And this tells me right here that I read 23 and skipped 0. Ouch. This means I got no row group elimination at all. I read every single segment for quantity and order date key to get what I wanted. And that stinks. All right, let's improve this. Here's what I'm gonna do. I'm gonna build a new table called big CCI ordered. I'm gonna create a table. I'm gonna put a classic clustered index on it. And the purpose of that is to order the data. If you have back data you gotta throw into a table, you either insert it in order or you supply an order afterwards. And so what I'm doing here is I'm gonna insert a mountain of data in one giant operation with a clustered standard B tree, whatever index on your transactional index. So add the index, insert all my data, and then I'm going to take and replace that index with the clustered column store. So because of this, the data is ordered. I did max stop 1 to ensure no parallelism occurs, because parallelism will actually take and insert your data in multiple threads, and that can actually kill row group elimination and misorder your data by taking it and inserting it in chunks in parallel. I don't want that. So whenever you create a Columnstore index, you want to actually max stop 1 it. And in this case, I do drop existing because I don't want to lose my data order. So I do that. It runs, it replaces my index, and now I have a Columnstore index on my table that is ordered because I ordered the data already. If I run my same exact analytic query from earlier, it comes back even faster. And I notice here now that I only did 35 logical reads off page. That's way less than 17,000 and still fast. And I can notice that I read 1 segment and I skipped 22. So I used the metadata in the Columnstore index and said, hey, your data is ordered. Let's see the ordered data. Here's the metadata from earlier again. You can see now the min datas and max datas they kind of lead each other through. This max is the min for the next row group, and so on and so forth. You see that like my values increase throughout the Columnstore index, right up until the end. And so at most, I'll never need, if you want data for a single date, I will never read more than 2 row groups at one time. That's awesome. So whatever date range I want, I'll get the row groups I need and no more. These may be lookup values, but you can see they're in order now. And this order is amazing. And more importantly, your data will be more efficiently stored. I'll show that in a little bit too, because I have more demos, but this order makes your data smaller, faster, and better in all ways. And so when you create a large Columnstore index, order your data and keep it ordered no matter what, going forward through time. That will make everything much, much faster and more efficient. Now, when I say, hey, create a Columnstore index and order it by time, this makes you think of partitioning a little bit, right? Classic table partitioning is an ideal thing for a Columnstore index because you're already ordering your data by time. Why not partition it too? Partitioning is very useful. That allows you to add some additional optimization so that when you read your data from the Columnstore index, you only have to actually physically read the partitions that have data you need based on your partition function. And so what ends up happening is time is probably going to be your dimension that you play with, and your data order will just match automatically with your partition function. You're done. This will reduce reads further. It'll make your queries even faster. And a big benefit of partitioning is all that maintenance-y stuff you do, all that operational stuff, like backups and partition swapping and partition truncation. Yeah, you can truncate a partition in an index, and poof, it goes away and you're happy. You can partition swap and load data in and out of an index, just like in a Columnstore index, just like anything else. You can do index rebuilds, reorgs, backups, all kinds of cool stuff, partition by partition. And that's great, because typically when you have a giant table that's inserted by time, the older data won't be touched as often. It may not be written at all. It's possible that once a year finishes, you may never write to a partition ever again. And if that's the case, you can do one giant rebuild and call it a day. My data's done. And that's great. So only do maintenance on the partitions you need to, and only back up the ones you need to if you need to. So partitioning gives you a lot of benefits, and we can demo it. I love demos. Demos are fun. So I'm going to I included the syntax here just so you have it. It's kind of helpful. Add file groups, add files, add a partition function by year, and add a partition scheme that maps my data to each file group based on these partition values here. And then I build a new table. This is going to be ordered on top of this partition scheme. I will create a classic clustered index. I will insert my mountain of data. I will then create the Columnstore index and replace the classic index. And now I'm going to go and run my analytic query again from earlier. And it's so fast now that I can't even perceive how fast it is. But what I see here now is I've gone down to 25 logical reads from 37. And this is a lot of rows, by the way. I'm getting a whole month of data from a giant index. And it says I read one segment and skipped two, because in that one partition, there's only 3 segments. And so I've made my data faster and more nimble than ever with all the maintenance benefits that partitioning offers. It all works in a Columnstore index just like a regular old index would. So feel free to partition. It's a great idea. There's a little bit of overhead, but once you've written the scripts to partition a table and do all that stuff to make it partitioned, you can really copy and paste those scripts for future use elsewhere, and it's very similar. And I'll freely admit that I have scripts that I copy and paste and reuse over and over and over. I'll admit it, it's faster, it's better, and I make less mistakes that way. And that's good. Reusing code is good. So huge, huge benefit. This makes your Columnstore index even faster, which is awesome. Cool. So best practice, do not update a Columnstore index. I mentioned it earlier briefly. The reality is that updates will typically be slow. And the more rows you update, the more segments you update, and the more row groups you update, the slower and slower it will get. If you update lots of rows, it'll be slow and expensive. And in fact, you can break a server doing this. You could take tempdb and bring your server down by doing this, and you won't even know you're going to do it. It'll just be slow, slower, slowest, and then broken. And so this is very poorly documented. There's some Connect stuff out there on it, but Microsoft does not have a plan of fixing this yet. Maybe they will, maybe they won't, maybe they'll document it, I don't know. But in general, don't update a Columnstore index. If you got to do an update, that's fine. Do delete and insert. It's cumbersome sounding, but it'll be way faster. And again, the biggest hazard here is you want to migrate some old code from classic slow table to Columnstore index. Be sure to check for updates. I was tricked by this one time ever, right? A server actually get like tempdb explode and a load process fail. And the fallout wasn't too bad. It was mostly just embarrassing because I said, hey guys, this is gonna be the fastest thing ever. I can't wait till it works. And then I broke the server. So don't do that. And it was all because I had one update statement that I forgot about and didn't migrate. So I knew there was a problem. I knew how to avoid it and I missed it. So be cautious of migrating old code and be sure that you don't have any updates. Next best practice is the same as best practice that we've always had in the database world, is query less columns. In general, query the columns you need and no more. If you need 3 columns, just get your 3 columns. Do not select star unless you have to, and aggregate over as few columns as possible. Every column you skip will be 1 segment per row group skipped. If I have 23 row groups, I will skip for each column 23 segments. If I have 1,000,000 row groups or 10,000 row groups, which is not out of the realm of possibility for a large table, I'll skip all those segments, which is amazing. If you have 10,000 row groups and 100 columns, you're going to skip millions of segments by simply skipping columns. So query as few columns as you need and no more. And it doesn't matter if you do them all in one query or not, just query as few as you need. So the next thing to mention is archive compression. Columnstore indexes have one more type of compression called archive compression. It is a super compression, higher compression ratio than other compression types. But it does cost more to implement, costs more resources to read and more resources to write. By resources, I mean CPU. So archive compression will make your data faster to read because it'll be tinier, and it'll use less storage, but it'll take more compute to write. So it's very good for data that's done, like your cold storage, your warm storage, your archive, rarely accessed data, the data you store for posterity, but may never really touch very much. And if you do, whatever, it can be a moment slower, who cares? So you don't typically use archive compression for everything, but it's great for scenarios where your data is not going to be touched much ever again, and it won't be written ever again. And because if you partition your table, you can select your compression type by partition. So you can say, hey, data from 2016 and earlier, I never touch. I'll never write to it ever again. Archive compression, done. 2017 and later, I will write to it occasionally, so I'll keep it regular Columnstore compression. And they're both very, very fast. Like, this is just more fast, but don't feel obligated to use archive compression unless you have mountains of old data that you want to make a little bit smaller. How smaller? You're going to ask. I would ask that question too. Don't trust Ed. You want to see data. Fine. I'll show you data. So I'm going to make one more table. I've made a lot of tables. Same idea as before. It's ordered data. And all I'm going to do, same thing as before, clustered index, insert a mountain of data, and then put a Columnstore index on with all the same parameters except data compression equals Columnstore archive. That's the only difference. Everything else is the same. Now I'm going to run my query from earlier to compare table sizes. And I do that. And I should turn off my execution plan. Whatever. It's all good. So there's my data. I can see here that I have a whole bunch of tables now. My original table was 5.1 gigs. My table with a covering index was a smidgen smaller, but not by much. My page compressed table got smaller. My Columnstore index got smaller. Now, this is the cool part. When I ordered my data, when all I did was order my data by the time dimension, did nothing else different. My data went from 343 megs down to 100 megs. I shrunk my data down to less than a third of what it was originally by just ordering it. And you're going to probably ask, how is that possible? How would ordering data make it more efficient? And the answer is that when you order your data, like values tend to pool together. If you take all the data on January 1st of 2020, that'll be very similar to data on January 2nd, 2020 as well. But it would be very different from data from January 1st in 2011. And so data, just by the nature of data, is very similar in close proximity to things date-wise. And therefore, when you take all your data and order it by date, you've now taken all your data and put very similar near it, and similar and identical data compresses better. And so by simply ordering my data, I sliced it down a lot. Archive compression sliced it down an additional 25–30%. So you do see a tangible benefit for archive compression. If you have cold storage, warm storage, data you never write to ever again, feel free to use it. It's pretty cool. It'll take longer to build and write it, but once it's written, it'll be awesome and save space. And so we've taken a table here and gone from 5 gigs of transactional data, 23 million rows, all the way down to 75 megs, 0.003K per row. That's nothing. So that's really the power of Columnstore indexes and the fact that you can take something so large and, imagine it wasn't 23 million rows. Imagine it was billions of rows and dozens of columns, hundreds of columns. This would take that and shrink it down to orders of magnitude tinier. So a few more notes I'm going to blast through before I finish. Again, feel free to ask questions at the end or contact me later for questions you have that aren't answered today. You might ask, well, how do I do index maintenance on a Columnstore index? And the answer is you may or may not have to do much. The things that cause fragmentation are unordered deletes. So if you delete from a Columnstore index and it's not off the end of it, it will slowly accumulate those soft deleted rows and it will consume space. And that is kind of like fragmentation. Updates will cause fragmentation because you will delete the row and reinsert it onto the end. So if you delete data from a year ago, you now have data from a year ago inserted onto the end of your Columnstore index with today's data. And that's fragmentation. Similarly, an unordered insert. If I said insert data into my Columnstore index right now from today, a month ago, and a year ago, that's fragmentation. But if your Columnstore index is ordered and you insert new data only over time, only insert and update new data, you'll keep a very, very tight index that will, in general, have very little fragmentation. So you won't have to do a lot of maintenance on it, or any, if you don't want to. And again, this is one of those performance things where if you see your index getting a little bloated, you can do a reorg and shrink it. If you think it's getting a little slow, you can perform maintenance. But in general, you won't see a performance hit unless you have a lot of fragmentation due to unordered deletes, inserts, updates. And your options are a reorg. A reorg is online, and it can forcefully process the delta store and get rid of it and compress it. It can combine undersized row groups. There are lots of little tiny old row groups that are residuals because of deletions. It can combine them, and it can get rid of your deleted rows for you once and for all, make them go away. So a reorg will do like 99% of what you need in a Columnstore index. The biggest piece, though, is that the reorg will not reclaim the space lost to fragmentation. So the ultimate change would be if you have a lot of fragmentation due to a release, a big change, a lot of unordered stuff going on, you may eventually want to do a rebuild. But again, if you have partitioning, you don't have to rebuild the whole damn thing. You can rebuild just the target partition, that was hit by your fragmentation, or do them one at a time. Again, reorgs are online. That makes them very fast. Rebuilds are online starting in 2019. Otherwise, you may have to pay the price of an offline rebuild. You can do a side-by-side, rebuild a new table and populate it and do all that stuff and then swap. That's slow as crap, but you can do it and it works. So ultimately, one thing you can do, some people do this, I do this occasionally, to get 100% optimal, is if I'm inserting data into my Columnstore index, I will run a reorg at the end. I will run a reorg right at the end to get everything out of the delta store into the Columnstore index. You do not have to do that, but if you like 0.1% faster makes your hair stand up a little bit, you can. It's kind of a cool post-processing step. You can do it. It's online. It's no biggie. So that's index maintenance. You can also have non-clustered Columnstore indexes. I don't spend a lot of time on it because realistically, separating Olap and OLTP is a huge deal. And when you combine them, you tend to have performance issues. And the same is true here. If you take a transactional table and put a non-clustered Columnstore on top of it, it's going to suffer from all the things that I talked about with unordered data and fragmentation and updates and all that stuff. You can specify a column list on a Columnstore index that's non-clustered, but it's very likely to be fragmented unless your data is very ordered and managed kind of in an Olap fashion. So a covering index might be good enough for your data. The ideal solution is to separate your Olap and OLTP, but if you can't, I highly recommend testing. If you're not sure whether a clustered, non-clustered, or covering index or whatever is better, test it. These are actually very easy things to test. You know your reads, you know your writes, you know your operations that do the things to your tables. Test it and see what's fast. Don't be afraid to build a new thing and hammer it. There's nothing wrong with that. But I caution that a non-clustered Columnstore may or may not be better. It might be, or it might not be. So I added here a additional index on this fact order big table. I put onto a non-clustered index, a covering index on a few columns, and off we go. So I go here and I run a query on it, and I note that it used the Columnstore index, the non-clustered Columnstore index, but I didn't skip any segments. And the reason is that this data was ordered by some order key, some integer identity thing. It wasn't ordered by date. So because this data is not ordered, row group elimination can't occur. And the Columnstore index may still provide some performance improvements for me on an Olap query, but I won't get completely optimal. Similarly, I can make a table up that has a regular old PK clustered table, put my data in and put the covering index of the column in it and say, hey, give me my date key with an include column. And I can turn my execution plan on and look at my query, and I'll note that it executed pretty fast compared to my original query. I can see that, here's how many reads occurred, like 1,500, and there's my execution plan. There's a nice index seek. So this is not as efficient as a clustered Columnstore would have been, but if you have a transactional table and you have queries like this that are very isolated and you can account for, a classic covering index might just be better. But again, test and be sure, because a column store index on top of transactional data will get very fragmented, and you may find that the writes are a little slower and the reads aren't as fast as you wanted. So testing really does tell you whether or not this is a good idea or not. So that's the end of my demos. I'm going to wrap up a few more points, throw it out for questions, and we can kind of finish up. So one thing people ask occasionally is, hey, can I put my column store indexes and turbocharge them with memory optimized tables? And the answer is probably not. Sometimes taking good things and combining them will not make a better thing. Column store indexes are optimized for Olap data, big, chunky Olap data. Memory optimized tables are optimized for transactional data, unordered, transactional, highly concurrent, lots of contention, reads and writes and locking and deadlocking and blocking and latching. That is where a memory optimized table is awesome. Combining the two rarely works. And in fact, the way structures are stored in memory, your column store index will probably be larger by an order of magnitude in memory than it would have been on storage. And therefore, a column store index in memory, I've seen one person propose a scenario, a hypothetical scenario, where it was actually good. It was for a random access table where they had data coming in and out fast and they wanted to do analytics against it. And for that one wacky, weird scenario, it actually was kind of good to do this. But in general, for 99.99% of the real world, you'll never want this and it won't help you at all. So don't consider it. If you think you have some application where you think it may be good, email me, we'll chat. Maybe you do. But most people never will, and that's normal. You don't want to really put these things in memory. It won't be faster or better. It'll just be weird, and weird is not necessarily good. And the last important note is that there, at the end of the day, is no free lunch. You have to read segments into memory to read data from a column store index. If I want to read 100 row groups and 5 columns, that's 500 segments that have to get read to memory. Now, I could use metadata once those segments are in memory to make the queries very, very fast. I don't have to necessarily read 500 segments worth of data to get what I need, but I do have to read those segments in memory though. So reading metadata and reading data requires getting all the segments in memory first. So to get optimal performance requires ordered data. If you partition it when it's big, you'll get improvements. Your partitions should not be tiny though. Somebody sent me a table like a few months ago where they had a column store index that had like 10 billion rows, but each partition was 100,000 rows. And it was really slow. And the reason was their partitions are too small. Ideally, you want to have maxed out row groups with 2 to the 20th rows. If you don't have row groups that big, you'll see no benefits of a column store index. So a partition should have at least 10, 50, maybe 100 million rows or more. In general, do a natural partitioning over month, quarter, year, whatever you naturally use in your organization, use that here, but don't make them too small. Load data via nice giant bulk inserts, avoid unordered deletes, and avoid all updates. And then rely heavily on row group and segment elimination through your ordered data. And the last note is have enough RAM to support your Olap needs. If you typically read, let's say, your most recent 6 months of data very heavily, have enough memory to store those segments in memory. Because if you're going to keep reading them over and over and your memory is running out and your buffer cache missing all the time, it's not going to be that fast. Again, no free lunch. Segments are still data. They're teeny tiny, but they're still data. They have to get into memory somehow to be read. So have enough memory to support your most common queries, whatever they are. And it won't be that much because these column store indexes are tiny compared to your classic tables. You won't need that much. That table I have with 23 million rows just now would have fit into 75 megs of RAM. That's nothing. Hey, sysadmin, can I have 75 megs? You're asking? Okay. And ultimately, just consider the size and shape of your output too. It's an important note that when you output analytic data to places for display in charts and graphs and analytics, make sure it isn't too big. If you have some dashboard that some executive looks at that has a screen with a line and you have 1 million data points going to a line, well, that's silly. You have a screen with how many pixels, not 1 million. So send less data, read less data, summarize it. But anyway, the wrap up here is that column store indexes can allow your analytic data to get really, really big and reside natively right in SQL Server in a place you're familiar, and you can put it right next to your transactional data or right next to Power BI or Tableau or whatever reporting systems you use. You can keep it all in one place. It's all included in your SQL Server license. You can make your Olap speeds really, really fast. You can make them reduce resource consumption heavily, which will make everybody happy, right? Whether your compute is in the cloud or on-prem or whatever, it'll make everybody happy. And again, they're not quite set and forget because there is order and there is fragmentation as an issue potentially. But if you manage it optimally, you order your data, you keep it ordered over time, you won't have a whole lot of maintenance to do, and it'll scale literally indefinitely. I've seen these things go up to the hundreds of billions of rows, no problem. No speed issues, no weird constraints in SQL Server, they're just fast. And so you can keep detailed data or analytic data and just keep building on it, and it'll be great. So that's everything I have. Does anybody have any questions about what I've presented and talked about? I know I went very fast. Feel free to ask questions or contact me later with anything you have that you want to talk about.
Yeah, Ed, I have a question about, so if you have a classic, let's say, star schema, and you've got in your case, millions of rows in the fact table, it's partitioned by date, everything's ordered. What additional indexes have you seen people use for the dimension tables and just keeping those joins as optimized as possible?
So here's what I would do. A non-clustered index on top of a clustered column store will be pretty hefty because it needs to build a B tree that points to all those little bits inside of all the segments. It's going to be very big and a little inefficient. When you first build a clustered column store, I would order it by time and avoid additional indexes at first. Because in general, if you filter all your queries by time, you will find that if you're running pretty classic analytic queries like sums and mins and maxes and that kind of stuff, that they're going to be really fast, really, really fast. They're going to use metadata, and the only latency you'll see is just getting those segments in memory for the first time. Once your data's in memory, it will fly. I would recommend no non-clustered index, but then let's say you do have some random report that runs and says, hey, get me data for each account and crunch it. Well, that's going to scan your whole index, and that might be kind of slow. If you find that those kinds of queries are slow or they're not returning data fast enough, you can then put a non-clustered on top that covers that query, and it'll make it fast. Just keep in mind that that non-clustered is going to take up a lot of space. So your clustered column store may take up, I don't know, a gig, but the non-clustered may take up an additional gig because it needs pointers all over the place, because you're taking your B tree structure and you're mapping it to this totally alien structure of column store stuff. So my recommendation is don't use them at first. Try running your queries without any additional indexes and see how they function. If they run good, which they probably will, you're set. Life is good. If they don't, consider additional indexing, but only after you've tested and confirmed that's the case.
Great, thank you.
I always say that in 95% of the column store indexes I've implemented personally, I have just had the clustered column store, done. End of day, life is good, ordered data, that was it.
And Chris asked a question in chat.
I didn't see it. Go ahead.
Yeah, just to confirm, if you cannot get the order correct, populate a table with a normal clustered index and then drop that and add a clustered column store index.
Yep. That is a perfect way of enforcing order the hard way, or brute forcing order by saying, hey, here's a clustered B tree. Put my data in order physically, just like this. Then you swap that for the column store. It'll keep the data in that order, and now your data is ordered. It's really either that or you trickle your data in, by date over time. That would also work. In my case before, I was kind of doing a cross join to generate a data set. So the data was scattered automatically over partitions, over dates, and so it was never ordered. So I had to have that clustered index, but you can similarly just say, hey, I'll build a new side-by-side column store index table. I'll trickle the data in starting with the earliest date through the most current date. And when I'm all done trickling the data in and everything's in there and it's ordered perfectly, I'll then just do SP renames. It's kind of a nice trick for loading up a new table and no one noticing downtime. Any other questions on column store indexes and how cool they are? Because I do think truly they are cool. This is a great feature. I use it heavily in my own universe of SQL Server, and I don't hesitate to use them anymore. I love them.
I have one question. How expensive are the rebuilds compared to your traditional clustered index?
Your rebuild is going to be the same basic cost of creating the index. You're building an index from scratch. It will require a lot of reads and writes. It will, outside of 2019, it will be an offline operation, so it'll block your table. I would only recommend a rebuild as a last resort. So you had, mountains of updates and inserts and deletes, and your table is totally fragmented and stuff is kind of slow, and you're reading too many segments. Do a rebuild. Or a common place people will do it is, let's say you write new data every day and that's it. So I go in every day, I load my data, or every hour or whatever, and I reload my new data. When you hit the end of a partition, you can then say, hey, you know what? My 2020 data is done forever. I will never write to it again. Therefore, I will go and do a full rebuild of my 2020 partition and then let it set and forget. Done. Because I will never touch it again. You can rebuild it with archive compression too, if you don't feel touch it very much in the future. But that's kind of the last resort. But in general, I try to avoid rebuilds. And honestly, I have Columnstore indexes I've played with that have billions of rows that I've never rebuilt once. And they're fine. They're great. As long as you don't do too much unordered stuff, you may never need a rebuild.
Very cool.
But again, you can measure fragmentation. You can go down and do the physical stats DMV to get some information on fragmentation, or you can simply look at the metadata like I did earlier and say, here's my row counts, sum them up, and then here is the sum of deleted rows, and then just check it out and be like, is this 5%? Is this 1%? Is it fraction of a percent? And then go from there. Any other questions about anything I've talked about? That's cool. If you think of anything later, feel free to contact me. I will email over as soon as I'm done the slide deck and the scripts. Feel free to share them and steal my code and use it in your own world. I don't mind anybody stealing my code. Just give credit, but feel free to steal. Stealing is good. And, any questions, contact me.
Great. Thank you so much, Ed. This was great.
Sure. Thank you very much for having me. I appreciate it. This is fun. I enjoyed meeting you, and maybe one day I'll get down there and visit you in person. That'll be a lot of fun.
Yeah, that's right. Okay. Well, thanks everybody. See you, Nathan.
Thanks,
See you.
Ed.
See you, Chris.
Have a good night, everyone.
Okay, we'll see you guys.
Bye.
Bye.